go over Dalton's atomic theory. Okay, and chapter 2 is also one of those very fundamental chapters that you need for chemistry. Chapter 1 was very fundamental in units and conversion factors, and then chapter 2 is very fundamental in learning about the atomic structure and nomenclature. It's kind of divided in 2 parts. Okay, so the first one, the atomic theory, I will not do a whole lot of this. Because this is part of your self-study, but I will just mention a few things over here for you. Dalton was not the first one. He's an Englishman. He was not the first one, though, to propose the atomic theory. Anyhow, a Greek philosopher was the first one who proposed this about 300 BC, about the atomic structure. And not the structure itself, but this is the concept of an atom. Okay, an atom is the smallest building block, okay, of anything. And he was the first one who suggested this, and he was just walking along the beach, and he just took some water in his hands, and when he was looking at the water, and as the water was flowing out, he realized that everything is still water. Okay, even though the volume of the water was getting less, it was still water. Okay, and that made him think about how everything is made up of, and he thought, okay, well, everything is probably consisting of small particles or small things, and he called it atoms. Okay, and then it was picked up by John Dalton so long after him. So then John Dalton came up with his 4 principles of the atomic theory. And the first one, he said that everything is made up of small particles called the atoms. Okay, and they're indivisible, which we know now is not true. Okay, because you can divide the atom up, except it's not the atom anymore. So in a way, it's still true. Okay, but it is the property of an element is given by an atom. Okay, and so he said, everything is made up of small indivisible particles. And then says that any element, okay, that you have is made up of one type of atoms, okay, in there. So, which means that if you have gold, then all the atoms in there are going to be of gold, okay, and nothing else, okay, in there. You can't have silver atoms in there. Dalton at that time did not know what the atomic structure was. Okay, what the atom itself was made of, so he couldn't say much more. But he said all the atoms in any element are alike, but we know now that it's not true. Remember what we were talking about last time about theory and laws and all that, and how you can change those things, and this is also one of those things. Okay, so the bigger premise hasn't changed, but still there were some changes because we got more information. Okay, so now we know that there are smaller particles than atom, and now we also know that within an atom you can have 2 different kind of particles. They both resemble the same element though, okay, but they're different kinds, which we will talk about. Anyhow, and then it's that a compound is made up of different kinds of elements, okay, in a certain proportion. And when you combine all of these things, they are combined in full atoms. Okay, it's not like you have something that is made up of half an atom. There's nothing like half an atom or a quarter of an atom. So when things combine, they combine in whole numbers, okay, with each other. When you have a reaction going on, these are all his 4 premises, by the way, all his 4 theories. When you have a reaction going on, in any chemical reaction, the atoms will rearrange to give you something new, okay? Which also kind of goes on to say a very important thing is that nothing is lost, okay, and nothing is created, which is also the law of conservation of mass, okay. So there are 4 things in here, okay. Everything is made up of small atoms. Atoms are alike in an element. This is very brief. Compounds have whole number ratio of atoms, and 4 in chemical reaction atoms will rearrange. gives to, I hope you can see, or maybe not, okay, I'll go over here, to the law of conservation of mass. Okay, and I don't know when it comes up, I think it does come up a little bit later. But the law of conservation of mass states that matter cannot be created nor destroyed, okay, at any point. So this goes with step number 4, okay, or law number 4, where he says that things are rearranged in chemical reactions, okay. And by the way, once the universe was created, the universe was created. That's it. We're done now, okay. The only thing that can happen in a universe right now is rearrangement of things, expansion, contraction, black holes, no black holes, whatever it is, that kind of thing can happen. But otherwise, nothing is disappearing from here, okay, or nothing is appearing also. Whatever is appearing, if there are new stars that are born, they're born from something else, okay. And so things are just rearranging themselves, and that's the law of conservation of mass, and that's a universal law, okay. So nothing goes away anywhere at all, okay. So that was the Dalton's atomic theory. Then the next thing, of course, is the atomic structure itself. This is completely something that you have to do as a self-study, so I'm just going to do this very, very briefly, okay? I will not take this too much, and of course, if you have your chapter summary, you have it here also. Okay, so you can look at this, and please, you should know the name of these scientists. They work really hard to give us all of this, so the least we can do is to remember them, okay, for all that they did. So the atomic structure, once the atom was kind of proposed by Dalton, then the next thing is, okay, then what is the atom made up of? And so what the atom is made up of was discovered by 3-4 scientists, and the first particle that was discovered was, anyone? Not was it? It was the electron. Okay, all right. It was the electron, all right, and that was the first particle, and it was discovered by somebody else, J.J. Thomson. And that's what I would like you to remember, at least about the scientist, is what they discovered. Okay, if you don't know anything about their personality, that's fine. Okay, eventually you might learn about that. Okay, but we don't cover that here. In any case, so J.J. Thomson discovered the electron. I provided some nice YouTube links for you on the class website. Okay, you may want to go on there when you want to kill time, especially after Thursday. When the exam is over, then you're going to have some free time. Okay, so it takes about 2-3 minutes. Just go through that and look at his experiment and what he did and how he figured out what the smallest particle was, which is the electron. What else is the property of electron? Anyone? Somebody, okay. Charge. They have a negative charge, okay. Very good. And I know this is a tough question to ask. Yes, you want to say something?
They have the least mass.
They have the least mass. I was going to ask you the number. Of course, you'd remember this, wouldn't you? Yes, of course you would. Okay. So the mass of the electron is 9.10938 times 10 to the negative 31, and this is in kilogram. Of course, that was on the tip of your tongue, wasn't it? Of course. So anyhow, that's the mass of the electron. So these are the things that you should know about the electron. What was the next particle to be discovered? The proton. So once the electron is discovered and you know that it's negatively charged, and we know that an atom is supposed to be neutral, okay, in charge, electronically it's neutral. So which means if you have something negative, you should also have something positive, okay, in there. So electron is the negative and here is the positive then, okay. So I'm going to write that over here. And who discovered the proton? Anyone? Come on. You should have done the self-study. It's even in the question. Yes? Right. From Australia. Okay, and he discovered the proton. And the proposal was there, of course, that you should have a positive particle, okay, but the fact that he actually proved it, okay, was the important part of it. All right, and the mass of the proton is 1.672 times 10 to the negative 27. Just the numbers, the exponents should give you an idea of how small we are talking about. Okay, negative 31, negative 27. It's mind-blowing. Okay, you can't even think of it. All right, it's such a small mass. It's very hard to think of it. Okay, so we have two particles, electrons and protons. All right, and the way we think about any kind of an atom is that the atom has weight. All right, and so the proton has larger weight than electrons. All right, so here is the problem that came, all right, with the discovery of the atom and all these particles that we're talking about, is when you look at something like hydrogen. Okay, hydrogen is supposed to have one proton. Hydrogen has one proton and therefore one electron. Okay, and the mass of hydrogen is 1, all right, which means the entire mass is coming from the proton. Okay, that's what it indicates. Electrons are considered to be pretty weightless. Okay, when we do the mass of any atom, we don't account for the electrons, okay, at all in there, so which means that the major mass is coming from the proton. Good so far? Now, going to the next element, which is helium. So helium is number 2, which means that it has 2 protons, which means it has 2 electrons, right? And so the mass of helium should be technically 2, but is it 2? It is actually 4, all right? So if the mass is 4, but the number of protons are 2, and electrons don't weigh that much, it means that there is something else in there. Okay, and so that something else obviously does not have a charge. Okay, because by the time we figure out the protons and electrons, the atom is electrically neutral. Okay, so if it's electrically neutral, then whatever is remaining is electrically neutral particle. Okay, so the last particle to be discovered then was neutron. And this was discovered by Chadwick, and this was the reasoning behind it. Okay, just what I told you, because of the mass discrepancies. If there was no mass discrepancy, then we probably would not have discovered it also. Okay, and so the charge is neutral, and the mass is the same as the mass of a proton. Yes?
That weight is equivalent to the 1 atomic mass unit.
That is where I'm going now. Thank you very much. Okay, all right. So instead of trying to remember all of this numbers, okay, for us, we just call this 1 atomic mass unit. 1 atomic mass unit. Electrons do not have a mass. So when we start learning about the mass of an atom, we do not account for electrons in there. Okay, they are 1,000 times lighter than neutrons and protons. Okay, the difference here is 4 zeros. Okay, so they're 1,000 times lighter, and so we don't even think about the electrons when we're thinking about the mass. Are we good so far? Okay, there was one other important discovery that Rutherford made. Anyone who's done your beautiful work, self-study work, tell me. Yes?
We discovered where the protons are located.
Thank you very much. And where are they located?
In the center.
In the center, okay? Because once you know all the particles, then you need to figure out where they are, okay? Where they are located as far as the structure is concerned. Now, the atom is found to be round, The first model of an atom, and you don't have to draw this if you don't want to, is that they thought that if the electrons are around here, the protons should be here also, all around, everywhere. And this was called the raisin pudding model. I hope it doesn't make you hungry, okay? But it's called the raisin pudding model because if you have raisin in pudding, then you never know where the raisin would come, okay? And so it's just distributed everywhere. By the way, just a little disclaimer over here, I write my electron as E minus, okay? I would suggest you do the same thing because E is the opposite of E minus, okay? Electron is a negatively charged particle, and when you learn more and more about chemistry, there is something called E, which is positron, okay, which is the opposite of an electron, okay? So it's positive electron, so that's why it's a nice thing to write the E with a minus, okay, on it, so you know you're talking about electron. So this was a raisin pudding model, and then Rutherford, of course, did his experimentation, which is called the
gold foil
experiment. Very good. And it turns out that there is something in the middle, okay, and that is called the nucleus. Very good. You guys are great. And the nucleus has the protons and the neutrons, and the electrons are outside. Okay, good. All right. This is now called the nuclear model of the atom. Okay. So what this really states is that the proton and the neutrons, which is the entire mass of the atom, is actually in the center, okay, of the atom. Electrons, which are weightless, it doesn't matter. They're all outside. Okay. Good so far. This is the nuclear model. As we go on and towards the end of the semester, we're going to learn more about where these electrons are, okay? What about the protons and the neutrons and the nucleus? You learn about nucleus when you get to nuclear chemistry, which is radioactivity and all of that, okay? Because if you think about it, when you have the same charges, do they attract or do they repel each other? Negative, negative. They repel each other, right? And if you think that, okay, we have a nucleus here and we have so many protons which are all positive, then how are the positives also close together? Because positives tend to repel positives, right? So if you have so many positives together, technically they should be repelling each other, which means that the nucleus should technically burst, all right? But that doesn't happen. Okay, so you learn that in nuclear chemistry as to why the nucleus actually stays together. Okay, so there are some other forces involved there. Electrons, on the other hand, they're happy campers. They've got this whole space, okay, where they can just move around, do whatever they want. All right, so far so good? Little bit of a perspective, okay, of what this would look like, okay. If you were to take a football field, football season started, right? Anyhow, if you take a football field, so you can imagine how big that is, right? And you take, okay, football for me is not really football, you know that, right? Okay, all right. In any case, and then you take a football or a soccer ball, okay, and you put that in the center of the stadium. Do you get your perspective now? Okay, that is an atom. Okay, so the outside space, that's where the electrons are. And the football or the soccer ball that's in the center, that's the nucleus. Can you imagine the spaces that we're talking about? Okay, so which means that the nucleus is really very, very tiny, okay, in there. Which means what also about the atom? What does that tell you about the structure of the atom? It's pretty much empty space, right? Because the electron is pretty much weightless, okay? So can you imagine just one runner in the entire football field running around? He's got the whole space to himself, you know, and all that. So, which means that the atom really is a lot of empty space because all the mass and all the particles are in the center. Good? Technically speaking, we are all made up of atoms, right? So technically speaking, you're all empty spaces. I'm very sorry to inform you of that. Okay, but yeah, you can do this, okay, and you appear as you appear because all the atoms are collected together and because of high density, okay, they're just close together. But otherwise, if you were look at yourself in an atomic model, you're just empty spaces, there's nothing else, okay, you're just, yeah, walking around, electrical fields, that's all. Good? That's the structure of the atom, okay? The nuclear model, which is what we're going to stick with, okay, for now. All right, a few other numbers that you should know about. Atomic number and atomic mass. By the way, I'm going to give you shorthand, and I already did, I think, in my own way. These are electrons, okay, you write as E, and then protons, P, and then N is for neutrons, okay, that's pretty traditional shorthand. Atomic number is the number of protons, okay, that's the atomic number. Today, I'm going to introduce you to all of this, and I'm also going to introduce you to the periodic table, okay, together. We do this hand in hand. So all the atomic numbers that you see are all the red ones on the periodic table, okay? Particles are never half or quarter, all right? Never, ever. So which means that all these red numbers that you see, these are all going to be whole numbers because you either have 1 proton or 2 protons, right? You don't have 1.5 protons. So it'll never be half a number. So all the red numbers there, the whole numbers, those are the number of protons. In a neutral atom, the number of protons should be equal to the number of electrons because everything is electrically neutral. Okay? Good. Now remember, protons are found in the nucleus, electrons are found outside. Okay, don't forget that part. Okay. Atomic mass is protons plus neutrons. Do you have a question?
Yeah. Is the mass number the same thing as the atomic mass?
Yes.
Because I've heard in the book it refers to both. It says
Yes.
both, and I was confused.
Okay. Yeah. Mass number, atomic mass, same thing. Okay. Yeah. And the mass number they say because later on when we get to compounds, you can call it the mass because it's a mass of all the atoms in it. Right now we're saying atomic because we're still at the atomic level. We're not at the compound level yet. Okay, so that is atomic number and mass number or atomic mass. Atomic number is given by Z, and atomic mass is given by M. If this is one information you would like to forget, I will have no problem okay, with that. So this is like one of the most trivial informations you can ever have. Yes.
I had another question.
Yeah.
With the atomic mass, you find them by adding the electron or the
Protons and neutrons.
But if you're only given like the electrons and you have to find the amount of neutrons, why isn't it like a specific number otherwise? Is that because of isotopes or like
Right.
why
So
isn't
we're
it just
getting
doubled?
there. You guys are reading ahead, which is really fantastic. Okay, but we're getting there. All right? Yeah. So hold on, just a few minutes. Okay, so when you have whatever kind of an element, okay, that you have, and you want to represent the mass number and the atomic number on that element, then you put them in very specific places. Okay, and again, this has to do with the language of chemistry. Okay, and again, when you do this, you learn this one time and you learn it very specifically. Okay, so if this is an element, element X, which by the way does not exist on the periodic table. Okay, so element X, there are 8 spaces on the element. Okay, over here as we write it. So there is a space here, there is a space here, here, and here. So all these squares on the corners of the element, they're for very specific things. Okay, you don't mess them up. All right. When you write a number there, they actually mean something very specific. And then the spaces on the sides over here, and here, here, and here, we leave those for something different. Okay, so later on when we get to bonding and all of that, then we're going to deal with these spaces. Right now, we're going to be dealing with the squares. Okay, so please make sure when you write all these things out, you write them properly. Okay, so let's say you have X as an element, the mass is written on the top, and the atomic number is written usually on the bottom. If you ever forget, if you ever forget which one is which, the mass number should always be larger or smaller than the atomic number.
Larger.
because it is addition of, exactly, protons and neutrons, right? So it should be addition of protons and neutrons is always going to be larger. So don't think you have to memorize this fact. Okay, so it's a very simple thing. The only thing that has the same numbers, top and bottom, is hydrogen. Okay, hydrogen is 1 and 1, but otherwise all the other elements, they're going to have larger masses. Okay, so you don't have to memorize and think, oh my God, the mass is on the top or is it at the bottom? Okay, so give your brain some rest, okay, at that point. Okay, so atomic number and atomic mass. Now for the question that you brought up, okay, regarding the numbers, okay, over here. So I mentioned to you that if you have the mass number, it's going to be the red one over here, which is a whole number, which it should be because it is protons, only protons, okay? But then it turns out that the atomic mass is not a whole number, even though you're adding the number of protons and you're adding the number of neutrons, right? Which really, if there's 1 proton and 1 neutron, that should give you 2, right? So it's not giving you 2.1. It should give you 2. Exactly 2. That's what it should give you. Well, that doesn't happen because if you look at the periodic table, then every single mass number that you have here has decimal points to it, which means it has fractions, okay, in it. By the way, one of the things that I have a problem with periodic tables, and I don't know whether they do this because of convenience, probably because of convenience, but when you learn how to write the mass number over there as an x, m over z, it's completely opposite over here, right? The atomic number is on the top, the mass number is at the bottom, okay? So when you look at any periodic table, you will see that happen because as today when we're going to learn about the periodic table, it's actually arranged chronologically according to atomic number, okay? And so they try to keep it on the top so you can see it nicely, okay, and easily. But otherwise, remember, okay, the mass,
But it's actually supposed to be.
when we write it like that, it's the other way, okay, as an element. But when you write it on the periodic table or when you see it on the periodic table, you will always see the atomic number on the top, okay? And that's why I said to you, you don't have to memorize what is the atomic number, what's the mass number, because all you have to look at the numbers, that's all, okay? Whatever is the larger number is your mass, that's it, okay? So don't get confused by anything else. Okay, so decimal point, everything has decimal points, okay, over here. So where do those come from? Okay, and this is where Dalton's atomic theory is challenged a little bit, okay, because Dalton said that in one element, all the atoms are alike, okay, in there. It turns out not so, okay, that doesn't happen, because that brings us to what we call isotopes. And in case of isotopes now, I think you said isotopes before. So in case of isotopes, we have the same atomic number, but different mass number, okay, of any atom. So which means that not all atoms are alike. There is something different about them, okay? And let me give you an example for hydrogen, because look at hydrogen. It has only 1 proton, technically 1 electron, okay? However, look at the mass. It's not exactly 1, all right? Which means that something else is going on, all right, in here. So hydrogen is 1, 1, hydrogen is 2, 1, and hydrogen is 3, 1, which means that it has 3 isotopes, okay? Now let's do the particle study on this one, the number of particles we have. For hydrogen 1, 1, we have 1 proton, 1 electron. Any neutrons? Any neutrons? Anyone? No? Shouldn't take you too long to think about this. What's the mass number here?
Protons plus
1, right? The mass number is 1, and so the entire mass is coming from? Just the proton. Just the proton. So are there any neutrons? No. No. So 0 neutrons, okay? And please don't be afraid, Okay? If it's 0, just say 0. Okay, it is 0. And I've got my class list here. I'm going to call out names, okay, if you guys don't talk. All right. So then over here, hydrogen, still the same atomic number, right? All of these are the same atomic number. So again, we have 1 proton, 1 electron. Do we have neutrons? Yes. Over here, 1 proton, 1 electron. Neutron? Good. And this is isotopes, which means that in one case you had 0 neutrons, one case you had 1, now you have 2, okay, neutrons in there. Now the whole question then becomes is, what is the ratio of these isotopes, okay? First of all, isotopes are naturally occurring. Naturally occurring meaning nobody creates them. You can create them too in lab, okay, which is what Marie Curie did, what is her daughter did, okay, Irene Joliot Curie. That's what they did, is they actually made some of these isotopes. But in general, there are a lot of elements that exist naturally as isotopes, which is why you have decimal points in all of these, okay, because these are all naturally occurring isotopes. So even these ones, these are all naturally occurring isotopes. So which means that they're already out there. So which means when you're breathing in hydrogen, which, you know, if there's any hydrogen here and you're breathing it in, it will have all of these 3 isotopes. The question is, what proportion?
So is the mass actually the average of the isotopes? Or is
Is it or it is?
Oh, I'm actually asking.
You're going to ask that? Okay, all right.
Is it the average of the isotopes?
So
Is that
it
why
is
it's
the
a-
average of the
okay.
isotopes.
So that's why it's a decimal.
Okay, very good. All right. So then you talk about the proportion. All right. So think about it as if you have 100% of hydrogen that you're talking about. In 100%, how much of it is 1, how much of it is 2, and how much of it is 3? So if you only have, say, 2% of this and you only have 3% of this, it means that you have 95% of hydrogen, which means that your maximum mass is still coming from isotope 1, which means that hydrogen 1 is the most abundant isotope, okay, out there. So if this is most abundant, the major mass is coming from here. What you tend to do is you take the mass and you multiply it by 0.95, which is the percent. Okay, so mass times the percent, and here mass times 0.03, and here it would be mass times 0.02. The masses that you get from this calculation, you will add them up. Let me go ahead and change this equal sign to addition. So now you have the percent contribution of each of the mass. When you add them up, you should get this beautiful number. Okay? Curiosity question. Anyone curious about anything? You should be curious right now. Yes?
What's the H and then the 2? Is that like 2 hydrogens or what is that?
This over here, this is the mass number. And this is the atomic number.
Right.
That's what 2 is. So H2 is not 2. This is we're just talking about atoms right now.
So is it bigger hydrogens than other hydrogens? Is that what
Maybe it's bigger, but maybe it's not. Because remember, when you have an atom like this, the mass is all centered over here. So what we're trying to say is that if you have a hydrogen, and here, if you have a hydrogen, 1 electron, and this one has only 1 proton, but in this case, you still have the same atomic size, but now you have 1 proton and 1 neutron, 1 electron. Here you have two neutrons, 1 proton, and still 1 electron. So the size doesn't change. Yeah, the mass changes. And remember, the mass is centered in the middle. Okay, all right, good. Yes?
Can we make artificial isotopes?
Yes, we can.
So we can there can be we can have isotopes that aren't naturally occurring.
Yes. That's what Irene Joliot Curie did. Okay, that she made artificial isotopes.
So you just put neutrons in the
You
nucleus.
could pump in neutrons, you could do whatever you want. Yeah, or take them out. Yeah.
Did you just make up those percentages?
Did I make up those percentages? Yes, I did. This is totally hypothetical. But that's where my curiosity question is going, actually. Okay, that I want you to ask me. Yes.
What are the other 2 boxes for?
What are the other two boxes for? We're going to come to that. Yeah, later in this chapter. Very good. Okay. My curiosity question that I would like you to ask me is about these numbers. How do you find them, right? That's the question, okay? Because I came up with it random, okay, just like that. But how do you really find those? You find them by using an instrument, okay, which is called the mass spectrophotometer. And the mass spectrophotometer picture is given to you on page 51. It's the most wonderful instrument ever created in chemistry. And it gives you the mass of anything that you want to know, okay? And so what we do is we put the sample through here. And it gives you information regarding each of the isotopes, okay, in there and how much abundance they're in, okay? So that's how you get the percent. And until the mass spectrophotometer was discovered, it was very hard to figure out the isotopes and their percents. And that's why Dalton couldn't do it. He didn't know about isotopes, so it's not really his fault, okay? At that time, he didn't have the instrument. But that's how you figure out all of this, which means that all of these elements were then passed through the mass spectrophotometer, and then the abundances were discovered, and then the calculation and all that good stuff. Good? Next curiosity question.
What did they do before they had that?
Hmm?
What did they do before they had that?
They didn't do much before they had this. They were working with round off numbers. Yeah. The next curiosity question is you have all of these numbers, right? Where you have all of these decimal points and all of these mass numbers, but then you have these ones, right? These ones are whole numbers, and they're also given to you in brackets. They're not given to you as like this, okay? They're given to you like this, and these numbers are they're different than these ones because obviously we don't know the isotopes of this one, okay? And that isotopes we don't know because these elements with the brackets, these are very unstable elements, okay? Which means that they keep undergoing radioactivity, which means that they keep losing particles. They'll either lose a proton, or they'll gain a proton, or they will lose a neutron, things like that, okay?
We can't find out how many isotopes they have.
You can find out how many isotopes they have, but because you don't work with them regularly like this, you don't have to worry about it. Okay? Yeah. But you can find out how many isotopes they have. You can also find out their abundance. The only thing is that abundance will change from today to tomorrow.
Is there a limit to how many isotopes?
No. There is no limit to how many isotopes, and there is also no way for you to tell how many isotopes something has. Okay? So I told you that hydrogen has 3 isotopes, and hydrogen does have 3 isotopes. But how many isotopes does calcium have? You will not know. And I will never ask you that. Okay? But you will not know that, and you're not required to know that either.
Will we only ever be able to know that hydrogen has 3?
You may not even need to know that. Okay? Yeah, because carbon has 4. So how would you remember all these things? Okay? By the way, I will tell you, hydrogen is a very special element. Okay? It's a very special element because it's the first element. It is also the lightest element. And there's one other unique quality in that it does not have a neutron. It does not have a neutron. Okay, so it's a very different kind of an element. Okay, and as we go on learning about the periodic table, you will see that hydrogen is very misplaced. Okay, on the periodic table, it's like, you know, I wouldn't say a stepchild, but it's like you really don't know what to do with hydrogen. Okay, and sometimes because it's just weird. Do you see hydrogen in 2 places right now on the periodic table? That's because we don't know what to do. Okay, and the periodic tables that I grew up with when I was studying chemistry, hydrogen used to be right here in the middle. Okay, so you don't put them.
Yeah, I would do.
Yeah.
So you don't put it on the left, you don't put it on the right, you put it in the center. Okay, because it doesn't belong anywhere. Okay, so it's a really weird element that way. And maybe because of that weirdness, I'm not quite sure, but whatever it is, but this is called hydrogen. Hydrogen 2 is also called heavy hydrogen, but it's also called deuterium. And hydrogen 3 is called tritium. Tritium. And hydrogen is the only element whose isotopes has names. Okay, all the other isotopes are just known as calcium-40, calcium-42, or sodium 24, 23, whatever it is. Okay, but hydrogen is very special that way. Okay, so its isotopes has names also on it. So far so good? By the way, I don't even realize that, but that was all your self-study. Okay, if you want to take 5 minutes and finish anything in your self-study, do you have anything to finish in there? Or no? We're good? I can continue? Okay, I will continue on then. Okay. All right, so now let's talk a little bit about the periodic table. Okay, so now you've learned about isotopes, you know about the particles. So now for the periodic table. Periodic table is very, very interesting. Next time when I come in, you will get a periodic table of your own. But right now, this is what you can do. Erase everything that you've written. Is draw yourself a very rudimentary kind of periodic table, like this. So you can write on that, okay, as we go along. Periodic table, very, very interesting tool, and a tool that we cannot live without. Okay, it was designed by Mendeleev. Dmitry Mendeleev, he's a Russian chemist, not long ago, about 100 years ago. Okay, that's when he designed the periodic table. And the first thing that he did when he designed the periodic table was that he designed it according to the atomic mass, not the number. Okay, as you go across the periodic table, the mass also increases. So he thought, okay, I'll arrange the periodic table according to mass. All right. The periodic table is divided into what we call groups and periods. So these, the vertical ones, these are called groups. And as you're going horizontal, these are called periods, or you can also call them row. In my world, and my world is a very nice world, by the way. If you stick with my world, you will be pretty good. In my world, these two over here and this block over here, this is called the main group. Okay? Okay. So that's called the main groups, which means that, or the main groups, not group, but groups, main groups. And the main groups is essentially how Mendeleev started. Okay, so if you look at the periodic table, there are 8 groups here. 1, 2, 3, 4, 5, 6, 7, 8. All right, so there are 8 main groups. All right, that's how Mendeleev got started. And by the way, when Mendeleev started, this periodic table was only half of what it is now. Okay, so 100 years ago, we did not know half of the elements on the periodic table. Okay, so he had very few elements to work with, and whatever he had, he put them in 8 groups. Why did he put them in 8? Because what he was trying to do is, when he was trying to take all these elements and put them in groups and rows, what he was trying to do was put all the elements that had the same properties in one group. That was his goal. Okay, so which means that if you have group number 1, these should have the same properties and not physical, chemical properties. Okay, physical will change. This group should have the same chemical properties, and so on and so forth. So it turned out that by the time he was finished working with all of that, it turned out to be 8 groups. Okay, and what he did is exactly kind of what you do when you start studying, is you take index cards and you write things out, and then you try to rearrange things, and that's what he did, and that's what he came up with. So the first periodic table was actually just a box. It was just like this. That's it. Okay, with 8 groups in it. And there were a lot of blank spaces in there because some elements had not been discovered. So even though he was writing elements in a group, there were some blank spots left in it. Okay? All you have to do is type in periodic tables in Google or historical periodic tables, and then you'll get pictures of it all. Okay, and so you can see what the first periodic table looked like, which was really not much. Okay, so then what happened is as the elements were discovered more and more, then the periodic table had to be rearranged, and then the middle part came, and this middle part, this is called the transition metals. And if you have colored pen, that's awesome. These are all the transition metals in the middle. So now the periodic table is divided into 3 portions for sure. The first 2 groups here, these are metals. This is the transition metals. And then you will see in all periodic tables, okay, whether, whichever periodic table you pick up, okay, there is a ladder that goes down like this, okay? So either it will be like this, or in that case, you can see that there is still a ladder starting from aluminum, okay, over here. So here is that ladder, okay, coming down. So this portion here is where the separation is for the periodic table. These are non-metals. These elements that fall in the ladder, these are called the metalloids. Metalloids are very interesting because metalloids have the properties of both metals and nonmetals. Which brings us to a simple question: what is a metal? And where is my pen? So, quickly, I don't have much time. So let's start from the back somewhere. What's a metal? Give me any one property of metal.
It's a solid.
It's a solid, except for
Mercury.
very good. Except for mercury. Very good. That's the only liquid metal, okay, out there. Very good. So they're all metals. Very good. Max, take away the next one.
All right. It's
Oh God, I heard that. Okay, next one.
They can be melted.
They can be melted. Now, I wouldn't put that one in there because you can melt anything. You can melt plastic also. Okay, but very good. Yes.
It's a good condenser of heat.
They're a good conductor of heat and
Electricity.
electricity. Very good. Anything else coming to mind? Huh?
They can undergo physical change.
They can, everything can. Yeah. What else? Can I take this and can I bend it?
Malleable.
Malleable. And I will write one more, they're hard. Okay? Almost all metals, almost. Okay, almost. Not all of them. Almost all metals are hard. You can bend any metal into any shape that you want, so it's malleable and stretchable and all that, and it's conductor of heat and electricity. They're shiny in general, and then of course they're usually solids except for mercury. Okay, so those are the properties of a metal. So which means that anything that does not have these properties is non-metal. Okay. Again, by the way, this is an exam question because you should know what the properties of metals are. Okay, it will come up again later on also. Okay, when we're going through the periodic table, we'll have to do this all over again and again. So, but in any case, so non-metals, metals. So which means metalloids that fall in the middle will have both of these properties. Sometimes it's very hard to distinguish whether you have a metal or a non-metal. What is it? So it behaves differently, and sometimes aluminum will behave like that too. Okay, is that you can't, it can behave both ways, okay, as a metal and as a non-metal. So it does conduct electricity, is shiny and all that stuff, but then sometimes it will do different things, okay, so anyhow, that's your first classification. The second classification is that some of these groups actually have names, okay. Okay, and so not all of them have names, thank God for that, but some of them have names, but you have to know the names of those. So for, this blue pen's not that great, let's take this one. So group number 1,
Alkali earth.
alkali metals. The first group is called alkali metals. The second one is called the alkaline earth right here. They're both metals, but you still call them alkaline earth metals or alkali metals. These in general, these are called transition metals in the middle. There's no other classification, okay, which is nice. And the transition should tell you that you're transitioning from metals to non-metals, okay? So you're kind of going there, so that's transition metals. Then the metalloids in the middle, no name for that. The last two names that we will have is for group number 7 and group number 8. Group number 7 is called halogens, and group number 8 are the noble elements. Yeah, and they're also called gases actually. You can call them either, I'm fine with that, because really group number 8, by the time you get there, those are all gases. Okay, so that's your classification of the periodic table. Okay, another curiosity question then. I did not mention anything about these two. Huh? No, they're naturally occurring. They are, yeah. It's, a lot of them are naturally occurring, but I did mention these two over here. Okay, so here's what we're going to do. We're going to admire the periodic table for a little bit. Okay, over here. So we're going to go through all of these numbers. So we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So everything is arranged chronologically. After 8, you turn around, you go back, and then you come back again. Okay, and so that's how the periodic table goes. Then I want you to look at the mass numbers also. Okay, and this is not something that you will do all the time. We'll just do it today, and then we'll forget about this. Okay, because technically speaking, when Mendeleev started his periodic table arrangement, he started with mass number. Okay, because he wanted to arrange it by masses, but it's not arranged by mass number. It's actually arranged by atomic number. All right, because what was happening, as I said to you, is that he was arranging it according to. Do you have a question?
No, I'm
No.
just stitching my arm. I'm sorry.
Okay, all right. So then what he was trying to do was try to get all the chemical properties, elements in one group. Okay, so when he went by mass, sometimes that was not happening. Okay, things were falling out of place. So he had to go back and check again, and it turns out that when he did it by atomic number, everything just fell into place. Okay, and so I want to bring to your attention maybe just 1 or 2 elements that I can remember that have weird masses. Okay, in which the mass goes down, because in generally the mass will also go up as you're going along chronologically, but say in tellurium and iodine, if you look at this, the mass of iodine actually goes down. Okay, so which means if he was arranging it according to mass number, these would be switched. Okay, but that's not what happened, because iodine, which is a halogen, has these kind of properties, okay, as that element. So that's why he had to kind of switch around. All right, so you will find a few elements like that on the periodic table, and again, I don't have it memorized, but there are a few other ones in here also in which suddenly the mass goes down instead of going up. Okay, but that's a very trivial information, and nobody will ever ask you, okay, for that kind of a thing. But it's there, okay, in case you're looking for it. All right, the other thing that I want to show you is right here, lanthanum and actinium. Okay, these are 2 elements. They go from 57 to 72. Okay, for the next one over here. And so 57 continues here to 58 down here. Okay, and so this is coming from lanthanum. So this is called the lanthanide series over here. And the next one, which is coming from actinum, this is called the actinide series then. Okay, so all of this. If you were to take the periodic table and you were to put all of this in the middle over here, the periodic table would probably cover the whole board, right? It would become that long. But then there would be so much empty space also, okay? Because right now there is so much empty space here as well. So if you put these two over here, there would be a lot of empty space here. Okay, so for the sake of arrangement, okay, and all of that, they're taken out. Yeah, they're taken out of it. They do belong in the periodic table. They're really not stepchilds, okay, but they do, they put them outside. Mendeleev got the periodic table started. However, he did not have all the elements, as I said to you before. Okay, he did not have all the elements he was working with. So which means that half of these elements were actually discovered afterwards, all right, that he made the periodic table. So the periodic table went through some rearrangements even after that, okay, and so the main group remained the main group, and that's why for me the main group has a different meaning, okay, and later on you will see that once you think of the main group as the 8 groups, your life will be so much easier, okay, and then think of the transition metals as different, okay, then your life will be a lot easier. And things will be easier to remember also. But coming back to the discovery of all of these elements, and also the whole theory of atomic structure, okay, everything that we will learn later on in chapter 8 and 9 about how the structure of atom is, that changed the entire design of the periodic table, okay, and so the transition metals got put in there, and then the lanthanide and the actinide series came, and so on and so forth. Okay, so a lot of discoveries then change things. Okay, so again, what we were talking about before with theory and law, you can change pretty much anything. Okay, provided you have good, valid information and data. So, but this is a new periodic table. One last thing I would like to mention that I would like you to start working on after Thursday. Okay, not before Thursday, because Thursday I would like you to prepare for the exam. But as you're getting towards the weekend and all that, I would like you to start learning the names of these elements. Okay, over here. These elements are what we call symbols, okay, that are written over here. You don't write hydrogen as hydrogen. You write hydrogen as H when it comes to the language of chemistry. Okay, so helium is represented by He, because obviously H is taken. We have about 117 elements now, but we don't have that many alphabets. Okay, so which means that some things have to change. Okay, over here. So what we do, and you will see that for all of this, is the first letter that you write is a capital letter. The second letter that you write is small. Okay? That is how you write a chemical symbol, an element. Okay? You do not write it like this. That's wrong. You do not write it like this. That's wrong. Are we good? You do not write it like this. That's wrong. All right? There's so many wrong ways of writing it. There's only one correct way of writing it, and that is this. Okay? For calcium. As soon as you start changing these symbols into something of your own handwriting and your own way, you change the entire meaning of it. Okay? So again, as I said, chemistry is a different language. Learn it properly. Okay? So you will see that elements, they either have the one letter symbol or they will have two letter symbols, and if they have two letters, the second letter is always going to be the small case. Okay? So please learn it that way. You have to remember some of these. So I'm going to go through with you a few of this. Okay, really quickly, if you could go with me. We'll start with hydrogen. Okay, and if you know the names, which you do know the names, okay, of a lot of these, so just go ahead and say it with me. It's like being in kindergarten, okay, but just bear with me. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium,
scandinavium.
Very good. Only one lone voice there. Okay, and then
Titanium,
vanadium,
chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium,
bromine.
bromine.
Oh man, awesome. Make us look bad.
But you're doing very good. I need you to know at least 36.
36.
Okay? You don't have to memorize as in alphabets. We had to memorize, alphabets.
Okay.
Okay, I mean like chronological order up till 20 or 36. I remember up to 20, but anyhow, you have to remember at least the names and the symbols up to 36. Okay, I can ask you that, and then some more. Okay, this is cesium, strontium, barium. Okay, whatever I'm saying, you have to know those. If you have a periodic table, you can circle all of those. You don't have to worry about this one. This one, only reason I'll mention this is because this is zirconium, which you might have heard of. Okay, and I don't know if you have or not, but in any case, don't worry about this one. The only element you will know over here is W, which is really weird. It is
Tungsten.
tungsten. Okay, very good, which is what you find in light bulbs. Okay, that's tungsten. By the way, SG, that's my initials. Do you have an element? You do?
No,
You small m? Okay.
It's samarium. All right.
Oh, samarium. Okay, very good.
Yeah, my name's Samarium.
There you go. That's your element. So find your element. It might be easy for you to
I don't
remember.
think my letter's actually on there.
J?
Yeah.
No, I don't think there's a J. No, there is no J. I'm very sorry. You don't belong in the periodic table. Here, osmium, cobalt group, iridium. I'll talk about iridium next time. Palladium, platinum, silver, gold, cadmium, mercury. I'm sorry, you do have to know some of these. Okay, over here. And then coming down to this one, you should know tin and lead, because we will talk about these quite a lot. You know iodine already. Okay, and iodine you'll be dealing with next week in your lab also. Okay, so iodine will come into picture then. Krypton you already know, that's where Superman came from. And then we have xenon and radon. Okay, over here. So you have to know all the noble gases. Okay? Yes.
I found they have a periodic table song on YouTube.
They
Yep.
do.
And it's very
Oh my
catchy.
God, you go for it. You go
It's
for
very
it.
catchy.
Yes, I
Like,
can't
I
keep up.
only
He goes
remember
too
the
fast.
lyrics up to, I think, Magnesium.
I don't even remember the
phosphorus.
tune. I just know he was so fast. I was like, I can't keep up with him. But anyhow, and regarding the lanthanides and the actinides, it's really going to be very hard for you to remember any of these. Okay, so I don't ask you to remember much over here. The only one that you might have heard of is uranium. We talk about it all the time as in atomic bombs, and maybe plutonium. Okay, and so those are the elements you should be aware of. There is an alphabetical list. I still have a few minutes, so hold on. There is an alphabetical list given at the back of the book. There it is. All right. Yes.
Does the spelling for the names count?
Yes, absolutely. Yeah. You cannot mess up the spelling. So best thing to do right now, okay, for the periodic table is to go online, or you can also photocopy this one if you want to. Well, this one doesn't have the names on it, okay? But go online, find yourself a periodic table that has all of this and the name of the element, okay?